Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back, dear students. As you know that in the last lecture, we started discussing the stability analysis of the power systems. And in the beginning of that lecture, I discussed the course contents, and also I went through the course learning outcomes, and I mentioned that we have at this stage covered the rest of, all the course contents, and the topic related to the stability analysis is still need to be covered. And in the last lecture I talked about the stability analysis, and uh, with today's lecture I will end the discussion on the stability analysis, as well as we will successfully cover all the course contents, and also the course learning outcomes. So in the last lecture I started discussing the power system stability analysis, and I also discussed an important equation known as swing equation. So in today's lecture we will continue with the stability analysis, and I will talk about the equal area criteria. But before starting today's lecture, let me quickly revise the contents of the last lecture. So we started the discussion with the point that stability analysis is important because power systems can be exposed to, or they could be subjected to different type of disturbances, where the disturbance can be, let's say, of a small magnitude or could be one of a large magnitude. That's why the stability analysis is mainly characterized into two types. One is the steady state stability and the other is the transient stability. So in the steady state stability we mostly consider small scale disturbances, for instance sort of continuous change in the load. And in the transient stability we consider large disturbances, for instance a fall or a sudden increase of a heavy load or removal of a load. So that's why it's important, because in order to ensure that all the machines they remain in synchronism with the rest of the system, because we have interconnected system, so it's important to ensure that the machines run in synchronism with the rest of the system. And during the application of the, let's say, a disturbance, the stability of the system need to be analyzed. So we started the discussion with the definition of the stability, and then we also discussed the two important categories of the stability. And afterwards, as I mentioned, that it's important to analyze this transient stability so that to know the conditions where the system can still remain in synchronism. So because if, let's say, the synchronism is lost, then under that condition maybe a part of the system, or let's say a machine can't deliver the power to the system, because for the interconnected system it is important that all the machine must remain in synchronism with one another. So if one of the machine is exposed to disturbance, and if it lose the synchronism, then that machine will not take part in the transfer of the power. So that's why it's important to carry the transient stability analysis to know the let's say condition under which the machine may lose the synchronism. So we started the discussion on the transient stability analysis with the two models of the generators, because stability is mostly related with the generators. So we discussed that we need both the models of the generator. One we call the electrical model, and all the other model is the mechanical model. So we, first discuss the electrical model, where we discuss that the electrical power, or the active power, it is related with the load angle. And this is the expression where the active power is sensitive to the load angle, and the sign term is also there in the expression. So we discussed first the electrical model, and then we started the discussion on the mechanical model, and we performed some mathematics, and afterwards we reach to an equation what we call the swing equation. So this equation, you and I discussed in the last lecture. It stated that if there is any change on the right side, there will be correspondingly change in the left side, which state that the angle will change. And if the angle changes, it will change the dynamic of the system. So, either we need to solve the swing equation to determine the points of operation, and the other method that we will discuss today, where we sort of intuitively determine whether the system will remain stable, or it will lose the stability, or it will lose the, let's say, the synchronism. So, we discuss the swing equation, and then for understanding the transient stability problem, we consider a simple case where we only took a machine connected to an infinite bus, and then we relate the swing equation to the mechanical and electrical power of the machine. So this is the mechanical power, that is the electrical power, or that is the active power of the machine, and this is the swing equation, where the dot on the delta angle represents its first order derivative, and double dot shows the second order derivative. So this is the right side of the swing equation, and that is the this is the left side, and that is the right side. And for determining the equilibrium points where the two powers are equal, this side, the right side, will be 0. So then we put that into 0, and we found the two possible points of operation, and we discussed that the angle on the left side of the maximum theoretical angle, which is 90 degree, leads to stable operation, while this point is it leads to unstable operation. We discussed that in detail, and then even afterwards we discussed that for let's say analyzing the transient stability of the power system, where disturbances can appear, and disturbances could be of various different types. For instance, as I discussed in the beginning, it could be a fault, it could be even an increase or decrease of a sudden load, because we are talking about the transient stability analysis. So we discussed that we need to carry the study of the power system under 3 different conditions. One is the pre-fault, one is the during the fault, and one is after the when the fault is cleared. So we also discussed that there are 2 possible methods of analyzing the transient stability. One is the numerical method, where a large scale power system is considered, and then the differential equations are numerically solved. The other method, what we call the direct or energy method, it is only applicable to a small scale power system where only 1 or 2 machines are considered. So they are mostly used for the small scale power systems. And we, in this method, the swing equation is not solved, rather it is an intuitive method, where based on the graphical representation of the energy, it is predicted whether the system will remain in stability or it will lose stability after the system is exposed to a transient, or after when it is exposed to a large disturbance. So these are the two methods of analyzing the stability. And then we, took an example of single machine infinite bus, where the infinite bus is connected to the synchronous generator via two parallel transmission line, and we considered that, let's say, there may occur a fault at this point. So then we discussed all the three conditions: pre-fault, during the fault, and after the fault is cleared. And all the three cases were analyzed. And the three profiles of the power were discussed, where we have during, before the fault, the profile looks like that, where the capacity of the system to transfer electrical power is more, because we have two parallel transmission lines, and that is usually employed in the system when, let's say, a large amount of power need to be transferred between buses. So if a fault appear, then during that time, and let's assume it's a short circuit type fault, so then during that time there will be no transfer of power. And even when the fault is cleared by, let's say, opening the circuit breakers, so one line is removed, meaning to say that the capacity of the power transfer will reduce. So we discuss all those three cases in detail. So in the last lecture, I talked about the stability in general, and then we, discussed the two models of the synchronous generator, because stability is mostly related with the generators. So we need to analyze whether after the application of a disturbance, the generator will lose synchronism or it will remain in synchronism with the rest of the system. Because if it loses synchronism, then it will not, take part in the transfer of the power flow. So that's important to carry this study, because we need to ensure that all the machines are remain in synchronism with the rest of the system. So we discussed in the first lecture, stability in general, and we talked about the swing equation, and then we also discussed some more concepts. So as I mentioned, that for carrying the stability analysis, one method is the numerical method, and the other method is what we call basically the equal area criteria. So now I have revised the contents of the last lecture, and now let's say we discuss the today's lecture, to end this discussion on the stability analysis as well as to end the course. So another method of analyzing the transient stability is through equal area criteria. What is this method? Let's talk about that, and then I will show an exercise or discuss a problem where we will understand deeply the application of such a method. So this method, as I mentioned even in the beginning, that it is related to the prediction of stability without solving the swing equation. So it's an intuitive insight, and it is based on the graphical representation of the energy without solving the swing equation. So this method is based on the graphical interpretation of the energy stored in the rotating masses as an aid to determine if the machine maintained stability after a disturbance, because it's important to analyze whether if a disturbance will appear in the system, and afterwards whether a machine or synchronous machine will lose the synchronism or not. Because as I mentioned, that if the machine loses synchronism, the power, it will not take part in the flow of the power. So it's important to analyze the stability in order to to check whether after a disturbance the machine will remain in synchronism or it will lose synchronism. So this method is applicable only to a single machine system. It's not applicable to large scale power systems. Although we will not go into the depth of that discussion But anyhow, it is only applicable to small scale power system where only a single machine or two machines may be involved. So now let's discuss this method uh, for only one machine connected to a infinite bus. So and let's talk about the swing equation and some more mathematics. So this equation we have discussed even before, and once again, this equation says that if there is any change on the right side, for instance, change either in the input power, because we are talking about the generator, and if, let's say if the mechanical input power is changed, then there will also be change in the angle, and that will change the dynamics of the system. So this is the swing equation. And now let's say we define an important quantity known as the H constant, or per unit inertia constant. So H is another constant related to the kinetic energy in the machine in megajoule at rated speed, and divided by the machine rating in MUA. So H is the ratio of the kinetic energy stored in the machine over the rating of the machine in MUA. The unit of H is second, and the relation between H and M is given like that. M is also a constant, is related with the H constant via this particular relation, where F naught is the let's say the frequency which lead to the synchronous operation of the machine. So now inserting 2 in 1, we get an expression, and the right side, the difference of these two power is equal to the accelerating power. Accelerating power can be positive, can be negative. If it is positive, it leads to the acceleration, and if it is negative, it leads to the deceleration. So now rearranging equation 3, we get an expression like that. So now let's say we multiply the expression equation 4 with 2 derivative of the load angle with respect to time. So we multiply equation 4 by this particular term. So we get the resultant expression to appear like that. And now this expression can be even written in this format. So after some mathematics, we get this equation. And now if we look deeply into this equation, it states that the change in the angle, so I discussed this angle even in the first lecture, and this angle, what we call the load angle, or it's also called the torque angle or power angle, it is the angle between the stator and rotor magnetic fields. So if a machine is running, let's say at a certain load angle, and if there, let's say, appear a disturbance, there will be change in this angle. And within this angle change, it will change the electrical power, because electrical power or the active power, it is related with the, it is sensitive to the load angle. So it will change the whole dynamics of the system. So as we are discussing about the transient stability, which account for large disturbances that could appear in the system. So if after a disturbance we consider or we analyze the system, so there will be change in the angle, and that will give us the relative speed. Because if the change in this angle is 0, it means that this angle obviously will remain the same. So if there is any disturbance, this angle will change. And if this angle changes, then the relative speed of the machine with respect to the synchronously revolving reference frame will also change. So now In order to ensure, let's talk about some concepts. This equation 7, it implies that for stability, the relative speed after some time of the application of disturbance to the machine must become 0. Otherwise, if let's say there is a continuous change or there is more change in the angle, as I discussed before, if this angle go beyond a certain theoretical limit, because due to the disturbance this will change, we will have a relative speed between the synchronously revolving reference frame, because you know that when a three-phase current is applied to the stator of the synchronous machine, it produces a rotating magnetic field, and then the rotor field and the stator field, they get locked and we have a synchronous operation. But if there is a disturbance, then the angle will change, and the change in the angle with respect to time will give us the relative speed between the rotor speed and the synchronously revolving reference frame. So in order to ensure the stable operation even after the disturbance, this must become 0. So now if this side after some time of the disturbance, if this side is 0, then the resultant equation looks like that. So this is what we call basically the stability criteria. So important point is that if disturbance appear, this variation in the angle after some time must become 0, because if it continuously increase, let's say, then the angle may increase beyond the theoretical maximum limit. They lead to the unstable operation, or they lead to the loss of the synchronism. I discussed that in the last lecture when I was talking about the two equilibrium points. So under any condition, this angle, let's say if we have a initial angle delta naught, so if there is any, let's say, addition to this angle when the load, when the disturbance is applied, so because there will be change in this angle, so this angle, let's say we called it, let's say delta steric, so that will appear when will we have the difference of the two power on the right side. So there will be change in the angle with respect to time, and if we add that to this value, then obviously this angle will change, and under no condition it must exceed pi by 2. Otherwise, and even this is the theoretical maximum limit. If it exceeds beyond 90 degree, then we have the slip of the poles, because then there will be no locking between the opposite poles and the synchronism will be lost, which means that that particular machine will not take part in the transfer of the power. So it will be sort of burden on the system. So we need to carry the transient stability analysis in order to check that what sort of disturbances the system can withstand, or what should be the amplitude of disturbance that a system can withstand without losing the synchronism. So the relative speed must be 0 after the application of the disturbance in order to ensure the stable operation. And if we put this side equal to 0, so we get this particular expression, and this states that the area under the curve should be 0 in order to ensure stable operation. In other words, the area under the acceleration and deceleration, we will discuss that, must be equal during transient stability for ensuring stable operation. So the two area will be equal. That's why this method is known as equal area criteria. So if the equal area criteria is let's say satisfied, the system will remain in a stable operation. So now let's talk about this expression and learn this particular method by working on an exercise. So now let's talk about this particular method and discuss that if the two areas are equal, the stability of the system is ensured. So let's talk about the method. Let us assume that, as we have already discussed the two models of the generator, One is the mechanical model, one is the electrical model. So now let's take the case. I mean, let's talk about the equal area criteria by let's say increasing the mechanical power, or let's say, I mean, one can explain it either way. Either we increase the mechanical power, that will lead to the change in the as we have discussed. If let's say we change the mechanical power, there will be change in the angle. Or if there is a decrease in the electrical power, let's say due to fault, or if there, I mean, is a decrease in the load, a sudden decrease in the load, there will always be acceleration power. So I mean, either way, either we consider an increase in mechanical input power, or we consider a decrease in the load, or we consider a fault. So under all those conditions, the difference of the two power will not be zero. We will have dynamics in the system that will lead to the change in the angle. So let's, I mean, work on an exercise where we consider an increase in the mechanical power to explain this equal area criteria. So let's, I mean, let's take the, I mean, let's discuss this method by considering an increase in the mechanical power in the mechanical power. So let's draw the curves, or what we basically call power angle curve. So let's say we have the power here, the angle, what we call the load angle on this side, and let's say, as we have discussed before, that the expression for the electrical power is equal to the product of the voltages. Let me find that page, so then we will discuss that. So the electrical power is equal to the product of the terminal and induced voltage divided by the reactance into sine of the angle. So let's say now we have an variation, and knowing that power is sensitive to the angle, rather sine of the angle, so sine of angle. So, and we know that, I mean, a power, it can be equivalent as P max sine of the load angle, where P max is equal to the magnitude of the EA into the terminal voltage divided by X, and then we have sine of the load angle term. So now let's draw this curve. Let's draw this curve, the sine of angle. I hope I have appropriately drawn it. But anyhow, this is the theoretical maximum limit, and that angle is pi. This is 0, and let's assume that the mechanical power is like that. So let's say this is the initial point of operation, what we call, let's say, delta naught. So let's say we have an angle before any disturbance, what we call delta naught, between the two fields, and then, as I discussed, that we can, I mean, explain this equal area criteria by either considering a decrease in the electrical power or an increase in the mechanical power. So now let's say we take the case where we consider an increase in the mechanical power. So the machine is running at this angle and the speed is synchronous because it's a synchronous generator. So at this particular angle, let's say, the machine is running before any disturbance at synchronous speed. So at this angle the speed is synchronous, and let's say there is a sudden increase in the mechanical input power. So let's call this as P m naught, and let's call this as P mechanical 1. So now if we look into the expression, the swing equation, if we look into the swing equation, it implies that if there is a change in the mechanical power, there will be accelerating power. As the accelerating power is positive, so what will happen? The speed will increase. We will have a relative velocity. So if there is a change in the mechanical power, we will have a relative velocity. So we will have a relative velocity. It means that the angle will increase, also the speed of the machine will go above the synchronous speed. So now at this point we were considering the machine to be running at synchronous speed, and let's say the initial angle is delta naught. So now if we apply the increase in the mechanical power, what will happen? The speed of the machine will go, it will increase, and with that the angle will increase, because as I discussed there will be relative speed. So the angle will increase. So now the machine will accelerate, and let's say it move in that direction. So then it will reach this particular point. As the angle advances, now at this point the angle, let's say we call it as let's say at this point we call the angle to be delta 1. So now we have an increase in the angle, and as I discussed that when the angle increases, because of the relative velocity, the angle will increase, there will be increase in the electrical power, and at this point now, at this particular point now, the speed of the machine is above synchronous speed. So now let's call this point where we start from, let's call this point as point A, this point is point, let's say B, and let's now this particular area, this area, and let's call this point as point C. So now this particular area will be called as, because the speed of the machine increases, so let's call this area A1 as accelerating area. So now let's take the integration of the area, or let's take let's calculate the area. So the area from the angle delta naught to delta 1, as we have already discussed that we discussed this expression. So let's now take from the initial angle to the angle delta 1, and now because Pm minus P will be positive in this particular area, so this, let's call this accelerating area, and let's take this as from delta naught to delta 1. Pm1 minus Pe d delta equals area ABC, what we call area 1. So let's say this area is area 1. Let's call this area as area 1. So now in this area, as I discussed that, because the machine accelerates, we will have a relative velocity, the angle will increase, with that the electrical power will increase until we reach a point where now once again the difference of the mechanical and electrical power is 0. But now at this point the speed of the machine is above the synchronous speed. So the machine will not stop at this point due to its inertia. Although the accelerating power at this point is 0, but because now the machine have a relative speed due to which it reached at this point, now the inertia of the machine will still keep the machine, to increase its angle. Although, as I discussed, at this point the accelerating power is 0, but because of the inertia of the machine, it will take some time, to reach, let's say now because of the inertia of the machine, the angle still advances, and let's say we reach this point. So now we reach this point, what we call, let's say, point D, and now let's say that is the angle what we call del max. This is the maximum angle, let's say. This is another angle. Doesn't matter what kind of note, you can use any notation you like. So now in this region, as one can clearly see now, at this region now the accelerating power, as we go beyond this point, then PE will be greater than PM. So, but due to the inertia of the machine, it will still advances, so the angle will increase, and now this whole area, let's call this as point B. So this whole area will be the deceleration area. So now the machine will decelerate, and at this point it reaches an angle what we call del max. So now at this point, if you look now at this point, because this is the deceleration area now, because the electrical power is now more than the mechanical power, which means that the relative velocity will be negative. So if the relative velocity is negative, it means that the machine will decelerate, and at this point now the machine is again at synchronous speed. So now we reach this point. At this point now the angle of the machine is del max, the speed of the machine is synchronous, but the machine will not stop at this point, because we have at this point still negative accelerating power. So even though the machine have now reached the synchronous speed, but it will not stop at this point. So what will happen, as the machine is the machine will now move from this point. Let me take another color. So now the machine will again move in this point. So now let me call this point as point, let's call this point as point E. So we will discuss that, but now as I discussed that at this point now the speed of the machine is synchronous, but still electrical power is more than mechanical power, which means it will still retard. So now if the relative velocity is negative, so now at this point we have synchronous speed, but the angle is the del max. So now what will happen, we will have a negative relative velocity. Relative velocity will be negative. So, and as the electrical power is more, so the machine will move back to this point. So now let's calculate even the area, what we call, this was the acceleration area. This is the acceleration area. Accelerating or acceleration area. So this was the acceleration area. Now if we find the area, we call this area as A2. So now the area under the curve from del to del max, PM minus PE d delta, we call it, let's say, area uh, B DE B DE, what we call area A2. So now, as I discussed that during the accelerating area, as we know that the kinetic energy is related with the speed. So during the acceleration, the kinetic energy will increase, and during the deceleration, this energy which is now stored in the rotating mass during acceleration, it will give up during the deceleration. And as I discussed that, in order for the machine to be stable, the stability criteria must be followed, which says that the total area under the curve must be 0. So now, whatever energy has been gained during the acceleration, the machine or the rotating mass must give it up in order to ensure the stable operation. And that is what we call the equal area criteria. The area, the accelerating area must be equal to decelerating area, or the energy stored during the acceleration must be given up during the deceleration. So now the machine will move back to this point. As at this point we have the negative accelerating power. So the accelerating power is negative, and if the accelerating power is negative, it means that the relative velocity will be negative. So now, once again, the machine will move from point D to B. But now at this point, we have, at point B, we will have the synchronous speed. But due to the inertia, it will still move in this direction until it reaches point A. So now it will move back to this point. Now at this point, we have angle del 1, but now the speed of the machine will not be synchronous. When it retarded, so at this point the angle was the speed of the machine was synchronous. But because we have a negative accelerating power, it starts moving in that direction. And now at this point, we will have lower speed than the synchronous speed. So now due to the inertia, it will still move in that direction until we reach at this point. And here again, when it reaches this point, here again we will have the positive accelerating power, and then it will move in that direction. So as long as the machine swing across point B, it will gain the kinetic energy due to acceleration, and it will give up that energy during acceleration. So the machine will swing across point B, gaining energy during the acceleration, giving up the energy during deceleration. So as long as these two areas are equal, so now according to the equal area criteria, we will have area 1 equals to area A2. So once again, if this condition is satisfied, where the machine give up the same amount of energy during deceleration as much as it has gained during the acceleration, so the machine will be under stable condition. So we need to find these areas and then check whether these are equal. If these areas are equal, then the gain of the energy during acceleration will be equal to the loss of the energy or the giving up of the energy during deceleration. So now with the help of this particular exercise, we have discussed the equal area criteria. And as I discussed at the beginning, that this method is basically based on the graphical representation of the energy rather than solving the swing equation. So if the two areas are equal during acceleration and deceleration, so then the stable operation is ensured. So now we have discussed this criteria even with the help of this example. So let me now quickly summarize the content. So in the stability, we consider two types of disturbances, because as I discussed that for an interconnected system, the machines must remain in synchronism. And as you know that, I mean, any sort of disturbance can appear in the system. So then we divide the disturbances into two types. One we call small disturbances, the other we call large disturbances. And as I mean the magnitude of the disturbance indicate that we need to more focus on the case where the disturbances magnitude are large, because as I discussed that if there is a disturbance, there will be change in the angle, and if the angle exceeds the theoretical maximum limit, the machine will lose the synchronism, and then that machine will not take part anymore in the power transfer. So in order to ensure the stability of the system or that of the machine, we need to consider the large disturbances, and we need to analyze the stability during the application of a disturbance. So we discussed that with the help of the Singh equation. We talked about the equilibrium points, and even we considered some examples where we discussed the system before a disturbance, during a disturbance, and after disturbance. And now in today's lecture, I discuss the other method of determining the stability of a system, and that is through equal area criteria, which is based on the graphical representation of energy rather than solving the swing equation. So now, I mean, once again, going through the course contents, we have now covered the power system stability analysis, and the objective related to that, or the outcome related to that, was that after the completion, the student should be able to perform stability analysis of electrical power system. So now I hope I have covered some contents regarding the stability analysis, and we have now covered all the outcomes as well as the course contents. So with this, I would end the discussion regarding the stability analysis, as well as we have ended the course contents successfully. So once again, I would say thank you very much for your attention, and I wish you very good luck for your final exam. Assalamu alaikum wa rahmatullahi wa barakatuh.